we're familiar, should be familiar, but want to mention it just in case, with the fact that if we multiply a matrix, 3 by 3 matrix, by the column vector C1, C2, C3, what we get can be written as C1 multiplied by the first column, 5, 2, 7, plus C2 multiplied by the second column, plus C3 multiplied by the third column. And it's clear that that's going to be the case because, of course, when we then add all this up, we're going to get, we're just going to get, and I can actually write it out, going to get a little bunched up, but it's 5C1 plus 7C2 minus 3C3. Now that's the first number, right? If we do those multiplications, we're going to get this number in the first row of our column matrix. Well, 5, 7, negative 3 times C1, C2, C3 gives us 5C1 plus 7C2 minus 3C3, just like it does here. And if you work out the second row of your column matrix and the third row by adding these vectors up, everything you get here is going to agree with what you would get if you did this multiplication. Okay? So what we get is a linear combination of the columns of the matrix. Now this tells us that no matter what we multiply the matrix, no matter what numbers we use here, we're going to get a linear combination of these three columns. And if these three columns are linearly independent, then that's going to give us vectors that span R3. Okay? The result over here, the set of possible results that we get by multiplying this by this, will span R3. If these three vectors are linearly independent. But if they aren't, then they're not going to span all of R3. Okay? If two of them are linearly independent, but the third one is linearly dependent on the first two, then we're going to span just part of R3. We're going to span a plane in R3. So, if three of them are linearly independent, you get all of R3. If only two of them are linearly independent, you're going to get a plane in R3. And if all three of them are linearly dependent on one another, you're going to get a line through the origin in R3. Just a line, not a plane. Okay? So what happens is your R3, okay, these would be like your C1, C2, C3 vectors. So here's where all possible vectors C1, C2, C3 live over here in R3, and that means that every point in R3 is going to give you one of these vectors, okay? And if you apply the transformation to all those points, then, as I said, what you're going to get over here could be all of R3. It could be just a plane through the origin of R3, and it could just be a line through the origin of R3. Of course, if you got all zeros in the matrix, it could just be the origin, okay? In any case, what you get is a subspace of R3. So I indicate this by saying, okay, you take all possible points in R3, and this blob here just represents all of three-dimensional space. And all possible points, you map over here, and maybe you get all of R3, but you're going to get at least some subset of R3, okay? Now, R3 is a subset of R3, so this subset might be all of R3, but it might just be a plane in R3 through the origin, and it might just be a line through the origin in R3. And it might even just be the origin itself. But to get just the origin itself, you'd have to have all zeros in this matrix. Well, that's kind of a picture of what we're looking at. And the thing you want to understand is that whatever you get over here is all possible linear combinations of the columns of the matrix that we're multiplying by. So yeah. There's more we can do, but that's the idea I want to get across. Okay? So S is the subspace of linear combinations of columns of the matrix. And this is a subspace of R3. And as I said, it might be all of R3, or it might be a proper subspace. The dimension of that subspace could be 0, 1, 2, or 3. Although a zero-dimensional subspace, well, okay, I guess it's kind of by default a subspace. But you'd want to check out all the subspace axioms, or the vector space axioms, to make sure of that. Most importantly, though, it could have a dimension 1, line through the origin, dimension 2, plane through the origin, dimension 3, the whole space R3. And again, as I said, this depends on how many vectors are linear combinations of the others. Okay, well, I'm going to put a couple more notes up here before I do the next segment.